Pluto is a far-off and secretive smaller planet that was once an individual member of our solar system. However, recent alarming declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They propose that this frosty world is on a potential impact course with Neptune. But how could this work out, and what might be the outcomes of such an enormous event? Are we seeing an intriguing galactic peculiarity, or is there something else to this looming, inestimable crash? Join us as we investigate the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet partly because of its unique orbit, remains a subject of interest and study in the galactic community. According to recent predictions by leading researchers, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential hazardous crash between these two planets, which could pose a gigantic threat to Earth. How is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires a stunning 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. But the interest doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, straying considerably from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unique is its inclination, calculated at 17 degrees to the ecliptic plane. The way Pluto follows its path is much steeper compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, challenging what we might expect from their positions in the solar system. This prompts the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its unique path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit does in fact cross Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of space mechanics. The three-body problem in space involves determining how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. For Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. The terms asu-libration and scope-libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is asu-libration. With regard to Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from intersecting. Scope libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an extra layer of protection from potential collisions. Another critical aspect in this situation is the VZK oscillation, named after three researchers, Vzel and Kai, who studied how objects move in space. It involves the way three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling influences how they move. For Pluto's case, the VZK oscillation helps us understand why its orbit near the Sun is so unusual. Despite Pluto's path seeming irregular, this oscillation helps keep it moving smoothly over long periods. The VZK oscillation shows that even though things in space seem chaotic and unpredictable, some patterns and rules keep everything in order. All of these factors help keep Pluto's orbit stable, ensuring that it doesn't crash into Neptune or stray off course. This three-body problem is key to understanding how these orbits change because of the way space objects pull on each other. Studying this helps us learn more about Pluto and our solar system, as well as distant worlds and their stars. Mathematical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is actually turbulent, with minor deviations in initial conditions leading to significant differences over thousands of years. However, these extraordinary properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the turmoil in check. Recent computer simulations have helped us understand how the large planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique connection with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's orbit consistent. However, Neptune isn't the only one at work. Jupiter's gravity also plays a large role in safeguarding Pluto's orbit. Additionally, Saturn helps as well. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for a long time, even millions of years. So it's as if Neptune, Jupiter, and Saturn are all working together to ensure Pluto continues to move safely in space without running into trouble. These phenomena are essential for maintaining order and stability in space. Without these mechanisms, the solar system as we know it would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable paths, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This gives a clearer picture of the dynamic nature of the solar system. The case of Pluto demonstrates how even the most seemingly unstable orbits can reach a state of balance through the complex interaction of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and investigation of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the strange nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computer simulations has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex math to model how Pluto and other space objects like Neptune pull on each other. By tweaking small details in the simulations, astronomers can see how even small changes can make a big difference in where Pluto ends up. In the late 1980s, these simulations showed something interesting about Pluto's orbit. Even though it has mechanisms like ASU libration and scope libration to keep it stable, its orbit can still be unpredictable and erratic. If you start with just a small difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after a number of years. But even with this chaos, Pluto's orbit remains stable over super long periods, like billions of years. This means that Pluto's journey around the Sun has a kind of order to it, even though it seems chaotic at first. Predicting celestial events, especially when they involve turbulent orbits like Pluto's, is a significant challenge. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While mathematical models provide powerful tools to understand and predict the future paths of celestial bodies, they also highlight the limits of our predictive abilities. These models depend heavily on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making exact predictions a daunting task. Moreover, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing and dynamic nature of the universe. While we've made huge strides in understanding space, Pluto's case reminds us how much our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have sweeping effects on the stability and direction of other bodies within the system. So why are major astrophysicists just now raising concerns about a potential impact between Pluto and Neptune? Despite all these complex forces trying to prevent such an event from occurring, Neil deGrasse Tyson, a prominent astrophysicist and a significant figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, especially the intriguing case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, offers insightful analysis on the evolving nature of celestial mechanics and the public's fascination with the unexplored realms of space. Tyson's position on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He views the renaming not as a downgrade, but as a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits such as Pluto's as a sign of how much there is still to discover in space. The intrigue of these unknowns is what keeps the exploration of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the future of Pluto's orbit suggest that we might still have many more mysteries waiting to be uncovered. Will Pluto crash into Neptune? Or is this another moment of confusion in the ever-shifting world of space? Only time and further research will tell. For now, we are left with a deeper appreciation of how much we still don't know about our own solar system. We continue to study these celestial phenomena in the hopes of uncovering more of the mysteries that lie beyond. The potential for a Pluto-Neptune collision raises just one more question about the unpredictable and fascinating universe in which we live. The possibility of a collision between Pluto and Neptune raises intriguing questions about the dynamics of the solar system, as it challenges conventional understandings of planetary stability. The notion that two celestial bodies with such dramatically different characteristics could collide is both alarming and fascinating, especially considering the current relative stability of their orbits. Given that Pluto is situated in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a powerful gravitational field, the implications of such a collision would be profound for our understanding of gravitational interactions and the evolution of the solar system. To comprehend the dynamics of a potential collision, one must first consider the composition and characteristics of both planets. Pluto, despite being a dwarf planet, contains a variety of elements and compounds that are thought to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere composed mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a giant gas planet, is composed mostly of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would have dramatic effects on their structure and behavior, potentially creating a spectacle that would be visible across vast distances. What makes this theoretical collision particularly fascinating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another crucial element. Jupiter's immense mass and strong gravitational field exert a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's domain. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it more unlikely that a catastrophic event will occur between Pluto and Neptune, despite the apparent risk. Recent research has also shown that the interaction between Pluto and Neptune is not as simple as a straightforward collision course. The gravitational resonance between the two planets, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a form of celestial lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while crossing paths in the vast expanse of space, have never resulted in a collision. The orbital mechanics of these bodies are fine-tuned in such a way that the potential for conflict is minimized. However, despite this stability, the long-term future of Pluto's orbit remains uncertain. As the solar system continues to evolve, subtle changes in the positions and gravitational influences of other bodies could disrupt this delicate balance. For instance, if the position of Neptune were to change over millions or even billions of years, it could potentially throw Pluto's orbit into a more chaotic state. This kind of instability could lead to a collision, or alternatively, it could eject Pluto from the solar system altogether. Astronomers have also begun to investigate the possibility that the outer reaches of the solar system may contain other, as yet undiscovered, objects that could influence the trajectories of bodies like Pluto. The discovery of distant objects like Eris and Haumea has already expanded our understanding of the Kuiper Belt, the region of the solar system beyond Neptune that is home to Pluto and other similar bodies. These objects may exert gravitational forces that alter Pluto's orbit in subtle ways, further complicating predictions about its long-term stability. In addition to the external gravitational influences, the Sun itself plays a crucial role in shaping the orbits of the planets and other bodies in the solar system. The Sun's gravity is the primary force that dictates the overall motion of the planets, and over time, changes in the Sun's energy output, such as the expansion of its outer layers as it approaches the end of its life cycle, could have profound effects on the orbits of distant bodies like Pluto. These changes could potentially push Pluto toward Neptune, increasing the risk of a collision. The ongoing study of Pluto and Neptune's orbits will continue to offer new insights into the complex mechanics of our solar system. As technology advances, astronomers are able to monitor the positions and movements of these distant bodies with greater precision, providing a clearer picture of their future paths. Despite the complexity of the forces at play, the probability of a collision between Pluto and Neptune remains low in the foreseeable future, but it serves as a reminder of the unpredictable nature of the cosmos and the mysteries that remain to be uncovered. In the end, the idea of a collision between Pluto and Neptune may be more a hypothetical curiosity than an imminent threat. Yet, it highlights the importance of continued observation and the need for a deeper understanding of the forces that shape our solar system. As we continue to study the interactions between celestial bodies, we gain not only a better understanding of the mechanics that govern our solar system, but also a greater appreciation for the fragile and dynamic nature of the universe itself.